Physics part 337. When using the equation F is equal to Bi into L sine theta, it is sometimes helpful to think of the term B sine theta as being the component of the magnetic flux density, which is at right angles or normal to the conductor. The Tesla is a lot unit for the measurement of the flux density. A strong magnet may have a flux density between its poles of a few teslas. The magnetic flux density due to the Earth in the UK is about 44 U Tesla at an angle of 66 degrees to the horizontal. The horizontal component of the Earth's magnetic flux density is 1.8 into 10 raised to minus 5 Tesla. The current in a horizontal cable is 150 amperes. Calculate for this cable, calculate the maximum force per unit length for this cable. Calculate the minimum force per unit length for this cable. Calculate them accordingly. In each case, take the angle between the cable and the magnetic field. Now it's your turn. The effective length of the filament in a light bulb is 3.1 centimeter. For a normal brightness, the current in the filament is 0.25 amperes. Calculate the maximum electromagnetic force on the filament when in the Earth's field of flux density, 44 U Tesla. A straight conductor, number 2, a straight conductor carrying a current of 65 amperes is situated in a uniform magnetic field of flux density 4.3 mt. Calculate the electromagnetic force per unit length of the conductor when the angle between the conductor and the field is either 90 degrees or 45 degrees. So you've got two parts of this question. Make your calculations for 90 degree and make your calculations for 45 degrees. So these are A and B. Force between parallel conductors. A current carrying conductor has a magnetic field around it. If a second current carrying conductor is placed parallel to the first, the second conductor will be in the magnetic field of the first, and by the motor effect will experience a force. By similar reasoning, the first conductor will also experience a force. By Newton's third law, these two forces will be equal in magnitude and opposite in direction. The effect can be demonstrated using the apparatus in the figure. It can be seen that if the currents are in the same direction, the pieces of the foil move towards one another. The pinch effect, as it is called, if the current are in opposite directions, the pieces of foil move apart. An explanation for the effects can be found by reference to the figure. The current in conductor X causes a magnetic field and the field lines are concentric circles. The field lines will be at right angles to the conductor Y, and so using Fleming's left-hand rule, there will be a force on Y in the direction of X. Using similar reasoning, the force on X due to magnetic field Y is towards Y. Reversing the direction of the current in one conductor will reverse the direction of two forces, and thus, when the currents are in opposite direction, the conductors tend to move apart. The force per unit length on each of the conductors depends on the magnitude of the current in each conductor and also their separation. Since force is